Here is another scenario. This time, the two components are in aqueous solutions. Form, solution. So how do we use the Henderson-Hasselbalch equation to compute when we prepare our buffer? Now keep in mind, okay, the individual concentrations of the two solutions must be equal to the desired concentration of your final buffer. So in this problem, for example, the two solutions are 0.5 molar and the desired concentration of the buffer is also 0.5 molar. Keep that in mind. So how do we use the Henderson-Hasselbalch equation in this type of problem? So let's write our Henderson-Hasselbalch equation. This time, you should be able to identify the conjugate base is HPO4 or hydrogen phosphate, and the weak acid component is the dihydrogen phosphate. Now, another thing you have to remember is that the concentration terms in our Henderson-Hasselbalch equation are the concentration in the final buffer, which means these are concentrations after mixing the two solutions. So we need to consider some dilution, right? So this is a diluted concentration. This is also a diluted concentration. So keep in mind, okay, since these are diluted concentrations, we have to use the dilution formula. With that, we will assign X as the volume of the potassium hydrogen phosphate and Y as the volume of the potassium dihydrogen phosphate. So we know that the final volume of the solution is 1 liter, which means X plus Y is equal to 1. The unit is liter. Now for the diluted hydrogen phosphate, we know that the initial concentration is 0.5 molar. And we are using X, right? X amount or X liter of this 0.5 molar solution divided by the total volume, which is X plus Y. So this is our formula for this final concentration of hydrogen phosphate. The same goes for dihydrogen phosphate. For this one, again, we have 0.5 molar. We will use Y liter of this 0.5 molar solution, and the final volume is X plus Y. So in our Henderson-Hasselbalch equation, we have our target pH, which is 7.1, and this was previously given in a former problem. So the pKa for dihydrogen phosphate is 7.2 plus logarithm of 0.5 molar times X over X plus Y divided by 0.5 molar times Y over X plus Y. And notice you can cancel out the 0.5 molar and also the X plus Y. So you are left with X over Y. And we have this relationship between the two. So we can actually solve for the values of X and Y. It's a system of two equations. So we have here point 1. This is negative 0.1. So that's so we transpose 7.2. So we get negative 0.1 equals logarithm of, so we have x and we can substitute y with 1 minus x. So getting the anti-logarithm of both sides of the equation, so anti-logarithm of negative 0.1 will give you 0.7943. And you have x over 1 minus x on the right side of the equation. Solving for x, you will get a value of 0.443. Again, the unit of our volume is liter. And it follows your y is equal to 1 minus 0.443. This is equal to 0.557 liter. Which means, so what volumes do we need to mix? We need to mix 443 ml of 0.5 molar K2HPO4 and 557 ml of 0.5 molar KH2PO4. So mix the two, check the pH with the pH meter, and again, if it's a bit different from our target pH of 7.1, we adjust it using hydrochloric acid or sodium hydroxide.